I want you to think of the Earth's atmosphere as a giant lake or ocean or swimming pool. And it's a large swimming pool filled with air. So, if we were to take a person and drop them into that swimming pool, because air isn't all that dense, they would sink to the bottom, and there's the person standing at the surface of the Earth. So they experience atmospheric pressure due to the weight of all of the air that's above them. So if we create a column of air above this person, then it's all the air that lies in that column pushing down on them that's creating atmospheric pressure. If it was just a square inch sitting at the surface of the Earth, then the weight of all that air that lies above that square inch would be equal to 14.7 pounds. If instead it was a square meter, then how much would it all weigh? Then the weight would be about 101,000 newtons. So we say that atmospheric pressure is equal to 14.7 pounds per square inch, or 1.01 times 10 to the fifth newtons per square meter. Well, what if the person wasn't standing on the surface of the Earth? What if they're in an airplane at great altitude? Then the amount of air that lies above them would be a smaller value, and the pressure would be less. And this is why airplanes have to maintain cabin pressure so that you don't feel the discomfort from the loss of atmospheric pressure. So what if this airplane, well, this would be a ridiculous example, airplanes don't fly this high, but what if the airplane was flying at an altitude of 100 miles? In other words, halfway to the top of the atmosphere. Then would the pressure at that point just be equal to half of the atmospheric pressure at sea level? It's a reasonable guess, right? Halfway up, half as much air. The problem is air is highly compressible, and so the density of air at the top is much, much less than the density of air at the bottom. And so the relationship between pressure and depth is nonlinear in the case of the atmosphere. So let's consider a different case. Let's say we have that same square meter sitting at the surface of a swimming pool. Then that pressure, we're calling atmospheric pressure, of 1.01 times 10 to the fifth newtons per square meter, or I'll call that a Pascal, is due to, like we said, the weight of all of the atmosphere pushing down on that square meter. In other words, the weight of all this air extending all the way up 200 miles to the top of the atmosphere. What happens when we take that object and put it at some depth underwater? Now there's an additional weight. Not only the weight of all the air lies above it, but also the weight of all of the water in this region. So the pressure at this point is going to be greater than the atmospheric pressure at the top of the pool. In fact, the pressure is equal to the atmosphere's pressure, the weight of all this air, plus the weight of all the extra fluid here, which is H2O, and then divided by area, right? Pressure, weight is a force, and force divided by area would represent additional pressure. In other words, we can say, let's give a new name to this. We'll call this the absolute pressure, because it adds up the atmospheric pressure plus the additional pressure due to the added weight of fluid. So we'll say that the absolute pressure is equal to atmospheric pressure plus this additional pressure, we'll call it gauge pressure. So plus PG. So in other words, this gauge pressure is just equal to, like we said, the weight of the fluid divided by the area, which means it's, let's see, weight, that's mg divided by area. In this case, we're imagining, I guess it doesn't have to be a square meter. It can be a square of any size. In fact, it doesn't even need to be a square. We could imagine if we had a rectangle of some length and width, it would experience atmospheric pressure at the surface. If we take that same rectangle and put it to a greater depth, then it has an additional gauge pressure on top of the atmosphere's pressure. So we can say this is mg divided by length times width. Let's see, let's come up with another way to express mass. After all, we were talking about the reason we sink to the bottom of this giant swimming pool filled with air that we call our atmosphere is because air has low density. But of course, the water in this swimming pool has much greater density. So how does density relate to mass? Well, density is just mass divided by volume. So that means mass is equal to density multiplied by volume. What volume are we talking about here? Well, if we're trying to find the weight of the fluid that sits in this region above our surface, then we're talking about the fluid that has a height of h, a width of w, and a length of L. So if we express this another way, gauge pressure is equal to density times volume times gravity divided by area, which is density times length times width times height times gravity divided by length times width. So we find that the area doesn't matter. Whether we had the full square meter, a rectangle that's not exactly 1 square meter in area, or even just our postage stamp, when all of those objects are submerged to the same depth h, their area cancels out, and the additional gauge pressure is just equal to the density times acceleration due to gravity, or gravitational field strength if you prefer that language, times h, which represents the depth within the fluid. And this density, of course, is the density of the fluid. If it's water, then the density is equal to 1 gram per cubic centimeter, which is the same thing as 1,000 kilograms per cubic meter. So if you swim in the deep end of a swimming pool, that additional pressure that you feel doesn't change with your orientation. You can go underwater in a vertical position or a horizontal position. It makes no difference as long as you're under the water at a depth of h, then the additional pressure you feel at that depth is the density of the water times g times the depth, so that the absolute pressure you feel is equal to atmospheric plus gauge pressure. So then the question goes, what should this depth be in order to make the gauge pressure 1 extra atmosphere? When would the pressure be twice as great as it is at the surface. So all we need to do is set gauge pressure equal to 1 atmosphere, and 1 atmosphere being the same thing as 1.01 times 10 to the 5th pascals. So rho GH has to equal 1.01 times 10 to the 5th pascals. That means H would have to equal 1.01 times 10 to the 5th newtons per square meter, divided by the density of water, which is 1,000 kilograms per cubic meter, and also divided by G, which is 9.8 newtons per kilogram. Hey, grab a calculator and see what you get. You should get a result of about 10.3 numerically. Now let's see what the units are. Kilograms cancel kilograms, newtons cancel newtons, and we can move the cubic meter in the denominator of the denominator into the numerator. So we've really got cubic meters divided by square meters, which is going to give us meters. No surprise, we're trying to solve for depth. So that says that for every 10.3 meters you descend underwater, you would experience an additional atmosphere of pressure. So if you wanted to feel an absolute pressure of 5 atmospheres, well, absolute pressure is already 1 atmosphere plus gauge pressure. So this would imply a gauge pressure of 4 atmospheres, which would then imply a depth of approximately 40 meters. And 1 meter is the same thing as about 3.28 feet. So, roughly speaking, for every 33 feet you descend underwater, there's an additional atmosphere of pressure. I want to check for your understanding this idea that pressure varies with depth. So out of the 4 situations numbered in the diagram here, which one or which ones would be impossible? We have 2 different fluids, one in red, one in gray, and we're not sure of their densities, but when you put them in a U-tube, their levels might settle out into any of these 4 diagrams. Okay, so make your pick which one or which ones represent an impossible situation. Let's start with number 3. If the density of the red fluid is equal to the density of the gray fluid, then the pressure at this depth H at the bottom of that section of the red fluid and the pressure at the depth H for this section would be equal if their densities are equal, and so equilibrium would be established and they'd level off just like diagram 3 suggests. The extra height beyond what sits below equal levels in our U-tube, this additional height of the gray fluid is not as much as the red fluid, so the only way that figure number 1 could be possible is if the density of the gray fluid is greater than the density of the red fluid. So comparing equal levels and looking at the additional heights of the fluid above that level, then we could argue in the same manner that figure number 4 represents a possible condition as long as the density of the red fluid is greater than the density of the gray fluid. But I don't think there's any possible way diagram 2 could exist unless somehow this red fluid had no mass or weight whatsoever. So that would represent the impossible case. In our next video lesson, we'll learn how an object, when submerged, has a buoyant force or a lifting force due to the fact that there's a variation in pressure with depth. If the top surface of this block has gauge pressure that's less than the gauge pressure at the bottom, that difference in pressure creates a lifting force, and we'll describe that lifting force as a buoyant force. So stay tuned.